My name is Jim Nitterauer. I'm a senior security specialist at AppRiver, now part of the Zix Corporation. Before we get started, how many are having a good time at NolaCon? That doesn't sound like it's very convincing. Come on. So if you see Rob and Eric and Yvonne, give them a big thanks, and all the volunteers, everybody wearing the red shirts. This is probably one of the best conferences I go to. I go to quite a number of them, and this one's really well run. People are hospitable. It's one of the best ones going, and it's really great camaraderie. So thanks for coming, and thanks to those guys for putting it on. All right, so today our talk is DNS strategies for reducing data leakage and protecting online privacy. Ooh, right? DNS. It's always DNS, right? Before we get going, disclaimer, the information I'm going to share today is intended for your use and to improve your security and privacy posture, not to be used for unethical purposes. We're going to talk about a few things that you could do, but most people in here are good. Everybody in here is good, right? I can do anything malicious. Concepts presented today are no way meant to imply original research on my part. Most of this is informational. The information presented here is gathered from public and private sources, and the views expressed are not necessarily those of my employer. These are some of the places I've spoken and some of the things I've worked with. I'm not going to spend a lot of time on this, but this is the article that kind of inspired this talk. Saw this article and was wondering how everybody's heard of net neutrality, right? And the lack of net neutrality and how that's no longer in play. So what does that give your ISPs and providers the right to do? It gives them the right to collect data, sell that data, and make a profit on that data without your permission or consent. How many people want that to happen? No, right? You want to know what's happening with your data, right? So one of the ways that they do this is that they look at your DNS traffic. And we're going to talk today about how that happens, what they do, and some strategies that you can put in play to prevent them from doing this. So what happens with some ISPs? Did you realize, how many of you are pen testers here in the room? Anybody ever do a pen test from a cable modem or a DSL provider and wonder why port 53 is always open on every IP address that you test? Interesting question, right? Not every server on the internet is a DNS server. Why would port 53 be open? Inbound, right? You find that on a network because your ISP is filtering and redirecting all port 53 traffic to their DNS servers. Another way you can tell very quickly, ever browse a web page on your ISP, the page doesn't exist and you get some search page for Mediacom or Cox or Comcast, whoever your provider is, how are they doing that? They're redirecting DNS because the DNS query failed to load the web page. They redirect DNS to their own response through their server and send you to their web page. So those are the kinds of things we're going to talk about today. I'm going to give you some strategies that you can look at for making your DNS more secure. So what are we going to cover? We're going to cover why is DNS important from a privacy perspective? What are your browsing habits that they can find out? What kind of internal service information can they find? This is both direct data that they can collect and what kind of data can be inferred from what they collect. Why should I care? Do you care? Maybe you don't care. I don't know, but there seems to be a lot of people here, so you probably do care. The data can be used for direct advertising, can be used for malicious purposes. We're going to talk about that in a minute. We're going to look at some of the common ways that DNS can be exploited via data privacy leaks. We're going to look at what sort of data might be leaked via DNS, as well as what information might be inferred. We're going to look at ways that you can track DNS data, either through logging or through packet sniffing. We're going to talk about a couple of odd things in DNS, this EDNS 0 option. We'll talk a little bit more in detail about that. Most people don't know what that is, but it's kind of a big deal. We're going to discuss insecure DNS resolution, what it is, how it happens, why it matters, and we're going to look at some of the leakage points in the DNS process. Then we're going to talk about some solutions. We're going to review DNS over HTTPS, which is called DOS, or DOH, I'm sorry, and the other one's called DNS over TLS, or DOT. We're going to describe what they are, how they work, compare and contrast them, look at some providers that offer that service, how you can set up some of your own services at home to use, take advantage of those services. Then we're going to look at some solutions for anonymizing your DNS traffic. Now, caveat, is security absolute? No, it's not. There's no such thing as absolute security. Security is only designed to mitigate the risk to a level that's acceptable for you, and everybody's different. Same thing with privacy. There's no absolute privacy. Privacy is what mitigates your leakage of data to a level that's acceptable to you. Okay, don't get those confused. There's never an absolute in both of those. So that's the premise of some of the parts of this talk. We're going to be looking at solutions to protect and anonymize your own DNS traffic if you want to do this, And we're going to look at some of the shortcomings that are involved with some of the new things, multicast DNS and IPv6, and we're going to look at some of the issues that might come about because of that. All right, so here we go. Why is DNS important from a privacy perspective? Well, it may not be critical to us living in the United States. We may think of it as an inconvenience. It may be something that people use to market to us. They may send us email. They may send us phone calls. How many of you get, I'm over 55, so I get calls from crazy spammers on my cell phone trying to sell me back braces and all this other crap that I don't need, right? So where did they get that information? How did they find out that I'm over 55? They bought that information from somebody, right? Maybe they got it from browsing habits at home. Maybe they see that I maintain my AARP membership. Yes, I'm an AARP member. Thank you. But it does have its benefits, good hotel rates. Anyway, for most of us, we just don't want people spying on our activity. But in some countries, in some parts of the world, people getting on the internet and what they do via the internet is monitored very closely, and it could cost them their lives, right? So it's a pretty important concept to understand how it works and what's happening. So we may have freedoms here, but these same techniques and strategies are being used to oppress other people in other countries to keep them from using the internet to its full potential. So we're going to look at some ways. How do we tell if our ISP is hijacking our DNS traffic? A quick search of the internet says it's pretty common, right? And there's searches out there that companies, they'll tell you that they're doing this, right? AT&T, we're turning your DNS logs into a money-making proposition, right? Are they returning that profit to you? It's your data. Are you getting commission for that data? No, they're making the money off of it. Well, what kind of information are they getting from a DNS log? Well, the typical stuff you can think of, they're going to get your WAN IP, the time of day, the domain you requested, the types of records you're requesting, maybe the servers that you queried along the DNS path, and some of the DNS responses. But why is it important? These are the things that they can look at. Some of the things that you don't think about is they can look at internal IPs. How many people have ever seen DNS logs from an external DNS server and you've seen Active Directory DNS queries in those logs, right? Well, if they happen to be text records or some other types of DNS queries, they might contain private IP information. They might be SRV records that are indicating what's happening on an Active Directory server in a network. That stuff should never reach the public internet, but it does. So that information could be out there. Data that can be inferred also includes email interactions. What type of mail servers are you interacting with on your network? What companies are you doing business with? Who are you sending email to? Email records in DNS also have SPF records, right? SPF records, sender policy framework records, that tell you what servers are allowed to send mail on your behalf. Pretty interesting way to give people that want to phish you and spam you a way to figure out how to hone their mail delivery to the right servers, right? They don't have to waste their time. They can figure out what servers are going to accept mail for this domain. Internal web applications. How many of you use things like Carbon Black or SonicWall or antivirus applications? Have you ever looked at your DNS that's outbound on your network from those applications? How do you think they do reputation services for domains that are being looked at on each individual machine? They hash the domain value, send it out to a DNS server that's hosted by the company. Let's say it's ESET, for example. They'll send a DNS request to ESET. ESET will get a value on that DNS request and send it back to the servers running on that machine. Now, do you think it's possible that some of those DNS packets may have other data in it besides just the request for the domain? Yeah, you're darn straight they do, and I'll show you where that's found a little bit later on. So, what other kinds of things can happen with DNS? Well, this shows you here how a man-in-the-middle attack occurs. You go set up Wi-Fi somewhere, you become the man-in-the-middle by ARP spoofing, and you become the router, and everybody routes their traffic through you. You could set up your own DHCP server and become DNS, right? I think that's kind of nefarious, right? That's kind of weird that somebody does that. Well, isn't it weird that your ISP does that very thing to you when you sign up and get service from them? How is it any different, right? You're at a coffee shop in your own home and you're wired and you don't even know it. It's basically the same concept, right? They're filtering the traffic and sending the traffic where they think it should go, not where you think it should go. These man-in-the-middle attacks are really not funny. The thing you got to figure out is whether you can trust your service provider's DNS. So, why should I care? There's malicious possibilities as well, right? It's not particularly easy to do at a network level unless you own the network. But it's pretty easy to do if you're on the network where the data is being transferred. Some other malicious possibilities. How many of you have gotten these crazy emails? Hey, we've got video evidence of you doing nefarious things on the internet, and if you don't pay us this ransom by X and X date, we're going to release this to your friends and your family. And we know your password, right? Because they've gone out into the dark web and found out passwords that you might have used in the past. So you get this feeling of, wow, somebody really knows something. Well, that's complete BS. They don't have that data. And you know that. If you're smart enough, you're not going to reply to this, right? But what if somebody is able to gather DNS data from what's been happening on your either home network, private network, cell phone network, Wi-Fi network? Maybe somebody at that network is doing things like browsing porn or doing things that may be a little nefarious. Now they send you an email saying, I've got this data on you. How do you know they don't have this data on you, right? You see how that can be used to get people to do things that they may not normally do. And it's pretty interesting the things that could happen in a corporate network if that ever comes to light. So could this browsing data be used to coerce somebody to do something? Yeah, it might be able to be, but these are just ideas about why leaking DNS data has some implications for your network security. So, where are the leakage points for DNS? How many of you use a product like Umbrella? Cisco's Umbrella agent, right? So that runs as an agent, it runs on SonicWall firewalls, it runs on a lot of different firewalls. That Umbrella agent is pretty nefarious and leaks pretty much data about every device that it's on, and I'll show you a little bit more information about that. But antivirus programs, endpoint security programs, they all will log and look at DNS data happening on the device that they're installed on. How many of you know that most browsers have built-in DNS stack? Didn't know that, huh? So, you wonder why Chrome's so fast. You load a web page, CNN.com, it might have 20 or 30 included domains. Your machine's not doing all those lookups on the network stack on your device. They're happening asynchronously through a different DNS resolver that's built into the browser. It's happening so fast you don't see it. But do you think they're not taking that DNS data? Do you think Google doesn't care about that data? Right? That happens in the background and you don't even know it. Because you can load a web page and you might see a couple of domains being resolved over the wire on your DNS if you're looking for just DNS port 53. But if you look at multicast DNS, which Google runs multicast DNS servers via UDP, they'll do this asynchronous DNS lookup in the background and cache it within the browser. And a lot of times it's done over DNS over HTTPS, so you can't even see it. It looks like regular web traffic. Okay, so you don't know what's happening. ISPs are logging DNS data coming off your network, obviously. And intermediate DNS servers also log requests. So DNS gets resolved from a cache server. If the cache server doesn't have the answer, it sends it through many, many hops over the internet till it gets an authoritative server, and then the data comes back to the cache server. At every step in that process, there is a point where data could be leaked to anybody that wanted to aggregate that data. So, again, this is kind of data that could be leaked. We talked about the basic stuff. This is basic log information. But if somebody wants to go to the extent of putting packet sniffers on the network, they could log everything that's within every DNS packet that leaves your network. Some of the included content, again, are the text records, the SPF records, DKIM keys. How many of you know how you authenticate a domain against Office 365? There's a special text record that you put a hash in your DNS, right? Well, somebody could sniff your DNS and potentially could they use that hash maybe to spoof you or spoof their network onto your Office 365 install? Not saying it's possible, but it's likely that they could with the right amount of effort, right? So you have to be careful about it. DNS is a great solution, but is it always secure? Is it always the best way to share information? Not necessarily. DNS information can also be added to DNS packets via the software on devices and sometimes on firewalls and proxies. One of the big ones, Cisco Umbrella, their agent puts, I believe, in the eDNS 0 packet, and I forget what the number is, and I'll explain this a little more in a little bit. They put the device MAC address, the local IP address, the device name, and a couple of other pieces of information. Sometimes the user that's logged into that device all get put in a DNS packet and a special record in that DNS packet and sent along with the DNS request out to the internet. Didn't know that, did you? Interesting how that happens. So, what kind of data could be leaked? This is an example here of an EDNS 0 client subnet packet. Who knows what EDNS client subnet is? Who's heard of it? Nobody. Okay. Well, you use it all the time and you don't even know it. How many of you use CDN networks? Content delivery networks, right? Used to be you had to proxy to a website that was closest to you. You had to pick it by location, geolocation, and do it by URL. Well, Google and Akamai several years ago came up with a way around that. It's called geolocation via DNS. And it's done via EDNS client subnet in a special DNS resolver that several of the major resolvers support. Google being one of them, Akamai, I think Cloudflare supports it. But within each DNS record, basically if you're an authoritative server and you've got, let's say you've got an east node and a west node for your cloud, let's say it's Netflix, and they got an east side and a west side of the country. They have two different IP addresses for those two sides of the country. When you resolve the DNS, it goes against the database that shows your information. This right here, that's the source IP. That's your WAN IP address that's packed into the DNS packet sent out to the internet. And it's in a special packet. I'll show you this in a second. When that gets to the DNS server goes, oh, that's geolocated on the East Coast. I'll return the DNS for the East Coast. And then you go to Netflix on the East Coast if that's where you live. That's a simplified way that it works, but it's much faster and much quicker than doing it via HTTP, HTTPS proxying. So that's how that works. But all of this information here is included in the payload in that one packet. I'm going to show you how that's structured in just a second. So this is actually a Wireshark capture of the EDNS option record for one DNS request. So in that DNS request, up top would be all of the regular DNS information. But this is down in the payload portion that's in the EDNS 0 option, or EDNS option packet. And right in here is the option code that's used. The interesting part is there's 65,533 different options that are available. There's only about 12 that are in use. So if you're into writing malicious code and you want to transfer data via DNS, that's the place to do it in the EDNS option packets. I'm not telling you should do that, but that's where you could do it. If you could write something that would read option 1595, you could send your data back and forth in those packets. Nobody would ever see it in DNS. They don't look for it. It would be completely stealthy. Nobody would ever see it. This option 8 is the number of the option. They're assigned 0 through 65334. That one's a RFC one. And that's the one that does EDNS client subnet. And it tells you the source net mask, the scope of the mask, and the client IP. That's the IP address of the WAN that made the request. And every DNS server will just simply forward that packet onto the next server. So it's in every DNS packet as it hops across the internet. This is a quick view of, it's a Graylog interface that we use to look at data on some cache servers on a very small ISP that we run kind of as a experimental thing. But basically, this is using PacketBeat as part of the Elk stack. You can install PacketBeat on it can be a bind server, it can be unbound. In this case, it's unbound. And it actually just sniffs all the DNS traffic in parallel, ships it off in a packet that Graylog understands, and then we can look at the data. And what this query here tells me, basically you can't read it, it's kind of small, but it's telling me, show me every packet that's leaving the internet, the connection to the DNS server that has EDNS client subnet data in it. And this is a very small ISP. I can't see the number, 300, 200, but this is every second. So every second, that information is being leaked out to the internet to upstream servers, and that just shows you that you can actually monitor it. So we'll talk about that in a minute. Other information that can be overlooked in DNS that you see if you were to log it or sniff DNS traffic are MX records. This infers mail habits, email habits. Who am I talking to? What customers? What places am I sending data? Who should I go after? Who should I target if I want to phish somebody? And also service provider DNS. What I mean by that is the ones that are doing your ESET and all of those kinds of things, the service or software that's on your machine. They're actually using DNS to validate the score of domains and URLs. So they send a specifically crafted DNS packet for every different domain or URL to an outside source and get a response back. Basically a DNS blacklist, an RBL list kind of thing. So this also can disclose to people that are looking at your DNS what software you have installed on your network if they know what to look for. right? And every vendor puts this out there. If you dig through their documentation, you'll find out. They don't advertise what they do, but if you ask, they'll tell you that this is the kind of information that they're using and how they're getting it out to the internet. So how is the DNS tracked? Well, your ISP or your local AD cache server or anybody in the path of your DNS will obviously log it. They can log the DNS through the regular log methods. Some firewalls log it, some proxies log DNS, local devices, third-party analytics log DNS, or you could do packet sniffing where you gather all of the DNS packets. A lot of times IPS and IDS devices do this, and ISPs will do this 100% because ISPs are looking for more and more. One of the big vulnerabilities or one of the big exploits that they see is data exfiltration via DNS. How many of you ever seen that on your network, what it looks like? You would know it when you saw it, but you won't look for it because it kind of flies under the radar. There's something called domain generation algorithms that most malware will use, and it'll generate random subnet or subnet domains for a normal domain. And it'll use these domains to send out over your DNS server. Most of them will fail, there'll be NX lookups, but a few of those will be the legitimate domain. They're actually registered. They have a name server on the other side. The name server responds with the proper piece of information, IP address, whatever the type record it's looking for. But the faraway mail or the faraway DNS server, the malicious one, does some other features. It reaggregates the data that's being sent as part of the subnet data or the record data over to that DNS server. So you can exfiltrate data from devices or do botnet command and control very easily using DNS. This is a typical DNS resolution process. Obviously, if a host requests from a cache server what the domain is, cache server has it in its cache, it goes right back. Nothing else leaves out to the internet. At some point in life, this cache server has to go out to the root server, get the root server, top level domain server for the domain. Let's say you're doing appriver.com. .com is the root. The .com root server knows that appriver.com is hosted by these two name servers. Then we have to go to those two name servers to get, well, actually the root server knows that the .com's there. Then we have to go out to the authoritative server and then back to the cache server, back to the local host. So there's 8 steps involved here. At every one of those 8 steps, DNS data could be leaked through that process. So you have leakage points on your LAN. So if you're on at your home network, you're probably not monitoring your DNS, right? I mean, there's probably nothing happening there. But if you're in a work network, if you're in a coffee shop, if you're anywhere where it's untrusted, you're probably having some sort of information gathered about your DNS that's happening. I guarantee you your ISP is monitoring, logging, and looking at all of your DNS data. The upstream cache servers probably are. The authoritative servers are. The root servers, they pretty much advertise that they don't do any gathering or selling of data. They will do it only for the purposes of logging and troubleshooting, and I don't think they keep the data for any period of time. That's part of their agreement with ICANN, I think, or IANA that allows them to be root servers. So they have some pretty strict requirements for what they can and can't do. So the root servers are pretty safe, but the rest of the servers in the path, not so much. So how do you secure DNS? Remember, security is relative. It's not absolute. So we're looking here from security, we're talking about privacy only, and the other part of it would be assurance that the domain that you look up is really, the response that you're getting is really from the domain server that should be handling that response. So there's 2 different things that are happening here. The ways that this happen are using DNS over HTTPS. This is defined in RFC 8484. Uses standard port 443 and a standard HTTPS connection with a normal HTTP handshake. Now, most of the implementations I've looked at of this are using TLS 1.3, which is a very new standard for TLS connections. One of the big differences between TLS 1.1, 1.2, and now 1.3 is the number of back and forth handshakes that have to happen before the connection is established. So with TLS 1.3, it's much faster because it does all of the handshake information in one round trip, essentially. So the initial client will send everything it needs to the server. The server will then initiate the connection, agree to the connection, and send back an encrypted connection with a handshake. Yes, now we can send data encrypted very quickly, whereas 1.1, 1.2, 1.0, you shouldn't be using 1.0, you shouldn't be using SSL 3.0, you should turn that off. You know, turn that shit off, okay? Be done with it. Turn it off, right? It's really bad. It's not a good thing. But anyway, I gave a talk a couple weeks ago on that, so I don't want to get off on that tangent. But anyway, TLS 1.3 is much faster and it's much more secure. One of the problems, and aside with TLS 1.3, is browsers will start to have support for encrypted SNI. SNI is server name indicator. So if you ever sniff packets on your network and you're using TLS 1.1, 1.2, you can tell the domain where that data is traveling back and forth, because that's the server name indicator packet. So when it gets to the remote server, you don't have to have an IP for every website you're hosting or every API. You have one IP and it's done by host headers. Well, TLS 1.3 has a built-in RFC for encrypting the SNI headers. So if you do any kind of packet sniffing or man in the middle for HTTPS, you can kiss that goodbye, because it ain't going to work with encrypted SNI headers. You'll never know where the data is going, and you won't be able to figure out where to get the certificate to be able to decrypt the data in transit to see what's happening. So this is a big deal. The other standard for DNS security is DNS over TLS. This is different. This is these two RFCs here, and it includes two pieces. So normal DNS traffic is UDP. This sets up a standard where you can implement datagram UDP over TLS, so more like an IPsec VPN tunnel instead of an HTTPS connection. Think of it that way. But the standard uses actually DNS over TLS. So all of the queries are sent over an encrypted TLS connection over TCP. So the server on the other side answers everything on TCP essentially. And it uses a standard port 853, and it's a TCP connection. So the two are a little bit different. When they both came out, of course, you had to have Twitter, and there has to be a pissing match about something, right? Nobody can agree on a standard because nobody wants to agree on things. So Nick Sullivan works at Cloudflare. He's one of the developers of this whole DNS over HTTPS, the DOH. And anybody know who Paul Vixie is? Yeah, the guy that invented Bind, right? So he's kind of the father of DNS. He now works at Farsight Technology, one of the president, founder of that company. And his comment obviously is, and this is a quote, this is actually what the tweet said, "It's a cluster duck for internet security. Sorry to rain on your parade. The inmates have taken over the asylum." So why would that be? Thinking it through, shouldn't DNS be secure? Yeah, maybe. But he has some points, and I think they both make good points about things. So what we want to do is look at contrast and compare these two different technologies. So DNS over HTTPS uses an existing port 443 and an existing protocol. Do you see any problems that might present if you're trying to filter DNS based on bad domain name lookups? There's no SNI in that. You can't see what they're looking up. You can't filter the DNS. You can't even see the DNS traffic, right? So now if you're infected with malware, how the hell are you going to tell if all of your network is using DNS over HTTPS to send DNS traffic back and forth to your cache resolvers? Now you have to do it on the endpoints. You have to look at DNS on the endpoints. So it hides the traffic in existing HTTPS traffic, so you don't know the difference between DNS and what's real HTTPS traffic. It's possible to do man in the middle because you can do inspection. Not every client right now uses the encrypted SNI. Once that happens, you won't be able to inspect it. It's hard to block just malicious domains without impacting the DNS process. It ensures reasonable privacy, but at the expense of a great deal of overhead, and it's slow. It's much slower than normal DNS. The other thing is it has caching issues. It doesn't use the normal DNS cache on your computer because it's HTTPS, right? So the DNS on a local device might get a query through DNS over HTTPS, but there's really no way to cache that information in a way that works well. The other standard is really, think of it more like standard DNS. It's just using TCP protocol and a dedicated port 853. The traffic is visible because you can look at the traffic that's happening over that port, but you can't see what's in the traffic because it's encrypted in a basically a TLS encrypted tunnel between the DNS server that's making the request and the DNS endpoint that's answering the request. Now keep in mind, this is not At this point, we're not talking about the client encrypting DNS on the network stack. We're talking about the DNS server that's being queried locally, making an outbound query to another machine that is doing it over an encrypted tunnel. Okay? We'll get to how we can encrypt it from the endpoint in just a minute. The full privacy is guaranteed if you trust the cache resolvers. Now, cache resolvers on the other side may log that information. So again, this is where privacy is relative, right? At what point are you willing to trust somebody to give you an answer that you're going to accept? Is basically the question. It's a whole lot less overhead, and it requires both the server and the client to rework their communications protocol. So how can I check to see if my DNS is leaking information? Typically, you think of DNS leaking when you're doing something like a VPN tunnel or doing something over Tor. But really, it can happen with any network. It's just a matter of what that data is being tunneled through. So one of the ways you can do it pretty quickly is use bind. If you're using bind for Windows, the way to do that is go to isc.org download, go down and download the bind for Windows. It's a zip file. Put it on your disk in a C:\bind, unzip it. You have to run this C++ runtime installer one time to make the program work. It doesn't install bind as a service, but one of the features of the whole bind package is that you can use dig on Windows. So quick and easy way to find out if your ISP is redirecting, filtering, or intercepting your DNS. Go to internic.net, pick a domain name, look up the name servers for that domain name. You would go, say, you're looking at Microsoft.com, and you know that there are name servers ns1.microsoft.com. So the question would be dig at ns1.microsoft.com space Microsoft.com. Enter. You get a reply back, and there's a flag field. And if you told dig to go to Microsoft.com, ns1.microsoft.com, and there's no AA flag in that record that comes back, you got a problem. That record means it's an authoritative answer. It came from an authoritative server. If your ISP or whoever you're working with is redirecting that request that you pointed at the authoritative server, it's coming back with no AA flag. That means you never reached the authoritative server. Some cache server intermediately answered that query on your behalf. That's a direct indication that somebody's screwing with your DNS. This tool Google put out several years ago. It's a great tool for comparing DNS speeds. It's called Namebench. You can get it at this URL, but it has a censorship check in there that will tell you whether your DNS is being filtered or redirected. So it takes a while to run. So, start it up, set the settings, run it, and then go to lunch or something because it will take a while, but it will give you some interesting results. An easier way too is, I remember I was talking if you're doing penetration tests or, go to Nmap, get Nmap, and you can actually just start scanning random IPs. If every IP you scan for port 53 has port 53 open, that's probably not a true reading. So that means, again, something in line between you and your target is redirecting port 53 to a device that has port 53 open, right? Because not everybody on the internet answers on port 53. There's some DNS leak tests here that are intended to test for leakage of information over VPN connections. But what they'll tell you basically is, are the DNS queries that are going out of my network from my browser, from my devices, are they actually going to the DNS servers that I expect them to be going to? And that's really all you're looking for, right? You want to make sure that the DNS queries are being forwarded to the location that you think they should be. And these are some 3 different ways that you can do that. All right, and the last way is to run Wireshark, and you can actually just set up a capture filter on port 53 or port 853 in case you're using encrypted DNS over TLS. And you also have to do port TCP as well because there's a new standard in DNS, not new, but it's been there for a while. But DNS servers that are RFC compliant need to answer on TCP as well because of the record size that could be returned. So sometimes you'll make a query to a DNS server via UDP. It will reply and say, I got that answer, but you got to ask on TCP because I'll fragment it if I answer on UDP. So you have to be able to respond and read DNS on TCP as well. Capture what's happening and see where the conversations happen. Wireshark has a feature up in the menu where you can look at conversations after you've done some captures on your network. So it makes it pretty easy to see where your DNS traffic is going on your network. How can I log my DNS? Doing all right on time here. One of the ways that we do it on our local DNS servers is we use Unbound on CentOS for some local cache servers, and we'll just use PacketBeat. It's basically a router. It sniffs and routes data from what it sniffs back to some log aggregation point. We just happen to use Graylog because it works really well. It does what we need it to do. It ingests the data. So what we do is we take this, we install it on our cache servers. One of the options is to set it to capture DNS, and then we export it to Graylog, and that was some of the information I showed you earlier. If you want to see more of this, hit me up and I'll be glad to show you some more detailed information, but that's a whole other talk that I do on looking at DNS data looking for anomalies in DNS data. So this way you can log and see what's going on in your DNS, what servers are talking to what requests are happening. It's good for finding out if you're getting a ton of NX requests, NX domain requests, those sorts of things. So now the next thing is, again, privacy is relative. How private do I want to be? Do I trust my ISP? Maybe I do. Maybe I've wasted your time here for, I don't know, gone on 40 minutes here telling you all about this stuff, and you just want to go home and continue to browse and share your data with the world. That's up to you. But there are ways that you can ensure that your privacy and the security of the DNS requests that you're getting are better than what you're getting now. One of the ways, Cloudflare, they had obviously 1111, and they announced that on what date? Anybody remember? It was April 1st, right? April Fool's Day. That was part of the whole joke, right? We're going to do this on April Fool's. No fooling. It's free, and we don't log anything. I'll talk a little more about the details here. They promised not to log anything for more than 24 hours, and I've talked to some of the people there, and I know some people that work at Cloudflare, and that they do that. They don't care about the data. They have no agenda to market. All they're doing is keeping the data long enough so they can make sure their stuff works. Soon after that, VeriSign came out with Quad 9. Their version of DNS is claims to block malicious domains. I don't know whether it does or not. I assume that it does. They support DNS crypt, and it supports DNS over TLS and DNS over HTTPS, as does Cloudflare. I just didn't put it in there. So how private do you want your stuff to be, right? So you could go to the extreme, and this is kind of the extreme. You could go to a cloud service provider, build yourself a VM in the cloud, use Unbound, configure it, and there's ways out there. This wiki tells you how to configure Unbound to use DNS over TLS to any outbound server, any cache server that supports it. So Unbound becomes your cache server for your network. And then what you would do is you would use a VPN or Tor or both to connect to that server for your DNS. And then that DNS would go out to the internet and answer your queries. But that would protect all of your DNS. The logs would only be gathered by the upstream provider that you pointed this machine to, whom you might trust, maybe Cloudflare, right? So you're reducing the leakage of data, you're reducing the likelihood, but you're not securing your privacy 100%. It's a lot of work to do that, right? It might be worth it if you need it. I don't know if it's the best approach, but you can mess around with it and see how it works. How private do I want to be? Opera, again, has a, how many of you used Opera? It has a built-in VPN, right? Anybody ever done Wireshark on that VPN when you're doing the data? I wouldn't trust it. First, there's no data encryption on that tunnel unless it's HTTPS to the web. So all of your DNS queries are going over that tunnel, the VPN, but they're all going to Opera, and they're logging every damn thing you do. So now you're trading one problem for another. Instead of selling the data, giving the data to your ISP to sell, now you're giving it to Opera's VPN provider. They log everything, and they make no bones about it. The company that does the VPN service is kind of a long, if you want to find out, it's kind of hard to figure out who actually owns the company that does the VPN service. So you don't know how protected that data is. The company is Canadian, but they're owned by a company out of Norway, which is owned by a company from somewhere else, so it gets very complicated. Bottom line is, it keeps your ISP from seeing your DNS queries, but then you're just trading one problem for another. Somebody else sees your DNS queries, and they make no bones about selling that and aggregating that data. So it doesn't hide anything. Firefox has no built-in VPN. It does, however, have a nice setting for configuring DNS over HTTPS. If you go into Firefox in the URL and type in about.config and then search for TRR, stands for Trusted Reverse Resolver. There's a bunch of settings in there, and one of them is where you can turn that on and you can have it send all of the data out to a Firefox or Cloudflare or any DNS over HTTPS provider that you choose, and now all your DNS queries go out to that. Okay? So it keeps your ISP from seeing your DNS queries, but it doesn't hide anything else, right? So it makes it secure in the browser, but now keep in mind you've got other software on your machine, Outlook or whatever mail program you're using, other programs that use DNS. So you're only hiding the DNS from the browser in this case. It's not hiding the DNS from your network. This is just a screenshot, and you can't see it here, but here's the TRR setting. It's modified. You set it to 2, and here's the DNS server that it's going to, and that's set to send all of the data through the browser to the encrypted DNS. You can actually go in here and you go into about.networking or about:networking, and you can see there's some interesting stuff. So you can see what you're actually browsing. How many know all this data is aggregated in your browser? Interesting, huh? So if you don't clear out your history in your browser, somebody can go into your browser, go into this about.networking, and see everything you've done on your network since the last time that you cleaned out your browser's cache. So keep that in mind. The Tor browser doesn't have that enabled by default, even though it is a version of Firefox or Mozilla. But this is Firefox, and it is enabled. So what you can see here is that this domain is IPv4, and the TRR is true, meaning that the DNS query was sent out to the HTTPS over DNS endpoint and returned that way. The other thing that it has, I just added this just so you had it in here, it will actually show you all of the HTTP requests that you're making, what port, whether it's HTTP2, whether it's SSL, and whether the connection's active. So it's a way that you can see what kind of security you're getting on your website. So I just threw that in there as an add-in. Tor browser will take all traffic, including DNS, and route it through a Tor proxy through several Tor nodes and come out some Tor exit nodes, right? So it's very secure, but you don't know what they're doing on that Tor exit node, right? You hope that the operators of that last Tor exit node that you happen to hit on that session are trustworthy. They may or may not be. You have no control over that. You can change who they are, but you have no indication of the path that they're going every time you start the Tor browser. So it does have settings for configuring the DNS over HTTPS. They don't stick. You have to set it every time that you go into Tor. You can view the activity again, and you can actually check in your browser. Go to this website, and it will tell you whether your browser is configured for TLS 1.3, whether it will work with DNSSEC, whether it will work with the DNS over HTTPS, and there's one other thing that, encrypted SNI, whether your browser supports encrypted SNI. So right now, most browsers don't support encrypted SNI, so it doesn't happen. So one of the other things that I didn't talk about much here, but it's implied with DNS over HTTPS, is that DNSSEC is always enabled. You can't disable it. So what is DNSSEC? The quick and dirty overview. Basically, if you operate an authoritative server for a domain, you have the option of turning on DNSSEC for the domains that you host. It means DNS security extensions. Once you set some keys, you have to go into your registrar and add one key to your registrar, set all the keys in DNS. Once they're there, somebody can make a query to validate that DNSSEC is enabled and that it's correct, so that when they make a connection to your DNS server, they can validate that there's a public key that validates that your domain name is coming from an authoritative server that has the key, right? So if DNSSEC fails, the thought is, well, there's two things that can happen. Either some server in line doesn't support DNSSEC validation, or they query some other name server and I'm getting bogus data. That's the problem with DNSSEC. Not everybody supports DNSSEC validation through the chain, so you can't always trust it that it's going to work. A lot of companies will say, we got to turn DNSSEC on, and anything that doesn't pass, we're going to turn off. We'll do that, and you'll have a really bad day with your company, because depending on who your DNS provider is, you may or may not get correct DNSSEC information from all the domains that are queried, because all of the end operators that do that don't always configure DNSSEC properly. So bottom line with Tor browser, keeps your ISP from seeing everything that goes over your browser, and it keeps all traffic secure until it goes out of the Tor exit node. So last thing, and I've got 5 minutes, so on time here. we talked about the endpoint not having every DNS query from that endpoint going through encrypted DNS, either over TLS or HTTPS. DNS crypt is a solution to the endpoint making DNS queries to another secure known endpoint. It was implemented both the client and the server. There's several proxies that you can download. You can either put a proxy on your network, or you can put a client. There's a Windows client that works. But basically, you put this client on a Windows machine, you do a couple of settings, and it takes over the DNS for that machine for every application on the machine and sends it to whatever DNS crypt compliant server you tell it to send it to, and it typically does it with DNS over TLS. So it's a way that you can make sure that all of the DNS for every application on that particular device goes through that endpoint. An easier way to do it, on my home network, I run pfSense firewall as my firewall behind my modem. On that firewall it runs Unbound. So Unbound has a setting that you can send all of your DNS queries to a DNS over TLS provider like Cloudflare or somebody like that. So I just send everything to Cloudflare, DNS over TLS, and none of my DNS data leaks to my ISP. So that's a simple solution. I don't worry about it on the endpoints. There's different ways of doing it. I'll keep it in the wrong key here. This last thing, how many of you have heard of TorGhost? One person. Wow. Okay. So if you want to be anonymous on your Kali box or a Linux box, this is an open source project called TorGhost. You download it from GitHub, you install it, you run it. It runs as a service on Debian, Kali. You run it, and it automatically changes your DNS resolvers and routes everything out of your computer through the Tor network. Every bit of traffic on IPv4. It shuts down IPv6 and sends all the data out over the Tor network. You turn it off, and you're back to the way you were before. So it's a good way of routing traffic away from your ISP or away from a coffee shop or something like that if you want to do that. So if you're browsing on the internet, it's a quick way of getting complete Tor activity for a machine. It's a pretty good little solution. So take-home message. These three technologies that we talked about today, they provide assurance that DNS isn't tampered with in transit. They do not ensure 100% privacy. Getting 100% privacy is cumbersome and basically impossible. In some cases, you end up trading speed for privacy. It introduces complexity and more points of failure depending on how complex you make your environment. And again, privacy is relative. What's your goal? Who are you trying to evade? And you cannot evade everyone easily. Tempered curiosity and paranoia are good, so validate your assumptions, make sure you know where your data is going, and I think we're about out of time. So that's going to be it for today. If you have questions, I will be happy to answer them for you. If you need any demos or want to talk more, I'll be here the rest of the weekend. So appreciate your time.